Taking a break from mole concept, we'll start off with electrolysis. In this setup here, the positive terminal of the battery is connected to P, suggesting that P is actually the anode attracting N ions. And the negative terminal of the battery is connected to S. This is going to be the cathode to attract your cat ions itself. And in the middle, we have Q and R. So for each of this beaker, it's important to know that you cannot have two anodes and two cathodes. So R would have been the anode, and for Q, it would have been the cathode. So the observation here is that for the case of Q and S, mass was actually deposited on it and there was no gas given out. In addition, the mass that was deposited on Q is much greater than that was on S. And we need to find out what is the reason behind that. And since both Q and S is actually the cathode, and we are also dealing with an aqueous solution, this tells us that H plus is actually present from water. But usually if we were to discharge H plus, hydrogen gas would be produced. But this time around, no hydrogen gas was produced. It means that the metal cation that was found in each of the beaker in cell 1 and cell 2 was actually selectively discharged. And what governs the selective discharge process at the cathode is a consideration to choose the cation that is the least reactive. And speaking of that, it's important for you to draft out the metal reactivity series to understand what is the potential position of the metals on the series with the shortcut of please, send, Charlie, monkey, and zebra in tall, lab, hunting cages securely gated with padlock. Now, the lower you go on the series, it has a higher tendency for selective discharge. But the higher the position on the series, it has a lower tendency for selective discharge. And since H plus is present in both of them, but yet it's not being selective discharge at all, it tells us that in cell 1 and 2, it could either be the presence of copper 2 plus ions, silver plus ions, or gold plus ions. So in A, I will say that this is not a consideration factor to say that both of them are the same, and we should not have even used concentration as a means of talking about selective discharge, because concentration is more towards the domain of anode selective discharge. For part B, it was suggesting that the cation in cell 1 and 2 is actually different. Now, we do know that for Q, it actually discharged more as compared to S itself. So, if I were to assume that silver plus ions was found in cell 1 and copper plus ions was found in cell 2 at Q, this is a half equation I should be looking at, which is silver plus ions gaining a single electron to become silver solid. But at S, it's going to be copper 2 plus ions gaining a total of 2 electrons to form copper solid. Again, understanding that this is a closed circuit, and as a closed circuit, the number of mole of electrons is the same, receiving at P, Q, R, and S. The ratio of silver to electrons is 1:1, but the ratio of copper to electrons is 1:2. We need twice as much electrons to discharge a single mole of copper as compared to only 1 mole of electrons required to discharge 1 mole of silver. So I'll say for per unit mole of electrons, 2 moles, maybe not 2 moles, twice the amount of moles of silver is discharged than copper 2 plus. And this gives the disparity in the mass that's collected, suggesting that B is the correct answer. But going on with the rest, we have them mentioning that the current flowing in 1 is greater than 2. This is again disproved because it's a closed circuit. The number of mole of electrons should be the same. And lastly, the loss of mass of P is less than the loss of mass of electrode R. Now this could not have been the case because P and R, they are actually anode. And since the anode is made of platinum, all inert anodes cannot oxidize themselves. And if they can't oxidize themselves, there is no chance for them to have a decrease in the mass. So once again, the correct answer for this question will be B because of the different identity of the cation ions. The number of mole of electrons required to discharge a single mole of them is different, leading to the disparity in the mass collected.